Okay, so for calculating your concentration of H2O2 or hydrogen peroxide for experiment 3, the reaction rate of iodine clock, the first thing, I'm just going to take trial 1, so you're going to have to do this. This is all of my data here in the times. The first thing you need to do is calculate the concentration of H2O2 for each trial, because you're changing the concentration for each of those trials. So this is just for one. So the concentration of hydrogen peroxide in your reaction is going to equal the moles of hydrogen peroxide over the volume of the reaction. So you can just add up all of the values across the table. So in this table here, it would just be the 2 plus 1 plus 0.5. So all of this here is going to count for the total volume. So we want to get your mils of hydrogen peroxide. This is for, again, trial 1. And to get that into liters, so that's 0.004 liters. So again, just doing a quick conversion here. And then to get the moles of hydrogen peroxide, you have the volume that you use times the concentration of hydrogen peroxide, and that will give you the moles of H2O2. So the concentration of the 3% hydrogen peroxide equals 0.88 molar. So that's what I have here, 0.004 liters times 0.88 moles per liter. And that will give us 0.00352 moles of H2O2. So again, the concentration in the reaction of hydrogen peroxide is going to equal the moles of hydrogen peroxide over the total reaction volume. So I have the 0.00352 moles of hydrogen peroxide over 11 mils, which is also equivalent to 0.011 liters. So this comes out to 0.32 moles per liter. Alright, so that's how you would get to the concentration of H2O2 so that you can put it into your graph. And then you're going to graph your data. So this is what the graph of my data looks like here. And if you can kind of tell, I'm just going to draw a line on top of here. This is not a straight line. It is decaying at not a constant rate. So the slope of each of these individual lines is going to be different. So if I look at the table on the bottom of page 30 here, just ignore my chicken scratches. This is, if it was, this is not linear. So is a plot of concentration versus time linear? No, so I'm going to go to the next one. So I have to plot the natural log of x versus time. So when I do that, I now get a straight line. This means that my reaction is first order, which also means that the rate for my reaction equals K, which is the slope, times the concentration of X. So here's my slope, the negative 0.161. X is the slope. This is, again, natural log of hydrogen peroxide in moles per liter times S in the time versus time, which is in seconds. Okay, so back to that. So now that I know that it's first order, this is the part E calculations. We have the target temperatures and then the times that correspond to that. So you're going to calculate the rate first, and you can use the equation rate equals delta H2O2 over time in seconds. This should have been calculated from part BC. This will be the same for all reactions. And that's because you did the 0.5 milliliters of hydrogen peroxide for all of these things here. I'm just going to do the calculation for trial 1 at 4 degrees. So the rate equals the 0.04 moles per liter H2O2. So again, this is from the trial 8, the concentration of H2O2. And you can just go back and look at your table there. And that was over 415 seconds. So my rate is going to be 9.6 times 10 to the negative fifth moles per liter per second. And then you can calculate the rate constant K using the equation from, again, the bottom of page 30, which is here. The rate equals slope K. So we know the rate, we're trying to get K, and then we know what X is. So we have rate times equals K times X, so 9.6 times 10 to the negative moles per second, and then K times this. So we're going to divide both sides by that, and then K equals 0.0024 per second. So you're going to go through and calculate K for each of these things, and then you will graph the K times temperature in Kelvin, and then you can observe what the line looks like. So it might be linear or exponential. That's going to be for you to figure out. Okay, if you're trying to figure out the calculations from part D, again, you have to go back to your graph to try to figure this out. So in my case, my goal time is 50 seconds. So you could eyeball here and go to 50 seconds and see that it is going to be natural log of H2O2 is around a little over -2. Or we can use the slope of the line, so y equals negative 0.0161x minus 1.0209. So I'm just going to plug 50 seconds in for x because this is on the x-axis and I'm trying to get to 50 seconds. So I plug 50 in and get y equals negative 1.8259, the natural log of which equals this. And then if you take e to each of those sides, H2O2 becomes, the concentration is, this is 0.161 moles per liter. So this is the total concentration of H2O2. So we know we want to have 0.161 moles per liter. That needs to equal some volume or some mole of H2O2 over 11 mils. We want to keep the volume the same as we did in the other reactions. So when you solve for x, you just cross multiply and divide. This is going to equal 0.002 0.00177 moles. And then you can multiply times the concentration of the peroxide, which is 0.88 molar. So this would be 1 liter over 0.88 moles. And this comes out to 2.0 mils. All right, and if we look back at our data, around 50 seconds was between trial 5 and 6, which was around 2 mils. So 5 and 6 was around 2 mils. That was around 2 mils of H2O2. Okay, so if you have any questions, just let me know.